Okay, so this is sort of a lesson to get an idea of basically what area under an IROC curve or instantaneous rate of change curve would mean. I think this should be review. So again, before you watch this, it would be great to try and do 1 through 7. You can probably do 1 through 7 on your own, just sort of remembering. But I'm going to go through it, so hopefully you pause, you do 1 through 7, try and do that on your own, and then check your answers. So practical meaning of area under a speed curve, that is distance traveled. If you think about a speed curve, maybe you say like, oh, we're going 20 miles per hour. Then this is time, so say we do that for, 10 hours or whatever, then this area right here would be 10 hours times 20 miles per hour. And that should give us 200 miles, right? So area under speed curve, that gives us distance traveled. Difference between speed curve and velocity curve. So velocity could be negative, right? Velocity could be negative. In other words, it has direction. So if you're moving to the left or down, it would be negative, whereas up or to the right would be positive. So there's a difference between finding area under a speed curve, which gives you total distance traveled, and area under a velocity curve. That gives you something else, because now it's counting the negative area in a sense. So area under a velocity curve is actually displacement, or how far you are from your starting place. So for instance, if you are doing velocity and you say, oh, I go to school and then I come back, your displacement is actually 0, right? But your distance traveled is, twice however far it is from to school. Okay, now we get into, so this is sort of the reason, the very, very basic reason of why we want to find area under a curve. It's not so much that we care about area, it's that we care about distance traveled, displacement, and in general, accumulation. So consider this function here, 0 is less than x is less than 6. That interval is partitioned or cut up into some subintervals with the following estimations of area given over under estimate of the area under the curve. So we're just trying to think about over and under estimates here. So if you use the function values on the left side of each subinterval as the heights of the rectangles, you would get so left side would be here, here, and here. So that would give us a rectangle like this. And that is going to give us an underestimate, clearly, because we're missing some area. On the right side, so then we'd be using that point, and that point. Now we're getting extra area. So we would get all of this stuff, right? So now if we use it on the right, that's going to be an overestimate. Repeat number 3 below. So on the left side now, that would be here, and there, and there, and there. So that's clearly going to be an overestimate. And if we use it on the right, we would start here and come here. So we're using the right side of each subinterval. That would actually be a rectangle of 0 area, and that's going to be an underestimate. So write a rule for determining whether an area approximation is an over or underestimate. So we could say if f of x is increasing, then what we call a right-hand approximation, in other words, using the function values on the right side as the heights of the rectangles. So right-hand approximation would be and let's see here, so if it's increasing, then the right hand was an overestimate because we took values that are higher, is an overestimate. while using the left-hand approximation is an underestimate. Okay, and pretty clearly the opposite would be true if f of x is decreasing, as shown in this example here. Okay, so that's sort of some of the basic stuff. I'm going to turn the page now. Great, so how might you improve estimations of area under the curve? So some things I think about is some more rectangles, right? If you have more rectangles that are overestimating or underestimating a little bit less, that would probably be better. More rectangles. We might use different shapes like trapezoids. Those are sort of the most obvious ones, right? So instead of having a rectangle like this, you might have, you know, a trapezoid that better models the curve. So a few things there. So this problem right here is just giving another idea of why we'd want to find area under the curve. So yesterday I actually did not give blood, but when I wrote this problem, this was actually true. So I gave blood, believe it or not. I was thinking about calculus while the blood dripped out of me. This is actually true. Graph below gives an approximation of the flow rate for my arm into their lovely pint bag. What do you think the area under the curve represents? Can you roughly approximate its value? So really, area under a curve, we're really multiplying this by this, right? We're really taking time in minutes and we're multiplying by blood flow rate, which is in milliliters per minute. So when we multiply those, the minutes are going to divide and we should just get milliliters. So basically what we're looking at is the total accumulation or total blood drawn in milliliters. So super helpful to look at units when you're talking about area. And estimating this, I mean, basically we'd probably make some rectangles here. I don't know, just cut this up here into some sections and try and estimate it. So let's see here, maybe I could even make a trapezoid here. And then let's see here, this one looks almost like a rectangle that goes up about this high probably. This one maybe looks like it would be about there. And this one maybe about, I don't know, there or something. So we can sort of use those. So this first one would be, remember a trapezoid is, I think you average the two. So this height right here looks like about, let's see, 20, 40, 60. So this would be about 30. So 30 plus, and this height looks like it's about, let's see, 40, 60, 65 maybe. 65 divided by 2. So that would be the basic average of the heights between these two right here. Then we multiply by the width, which is 2. So that gives us the first one. Second one is 2 times, looks like the height is maybe, I don't know, 82. Third one would be 2 times, maybe, I don't know, 65. And then the last one, 2 times, so let's say 70. So that these twos divide, you get 30 plus 65 plus, 30 plus 65 plus 164 plus whatever this is, 170 plus 140. So this should be 95 plus 300 plus 104 plus 70. I'm breaking this up in a really weird way, but that's fine. So that should be, 300. We'll just make that 200 right there. So 570. So somewhere around 570 milliliters, but that's an estimation. Okay, so I'm going to pause this video because that's sort of the introduction so that I can start a new one for the more mathy stuff that comes later.